radio frequency radiation can be used to connect and power wireless devices simultaneously, enabling them to become battery-free. Simultaneous wireless information and power transfer, or SWIPT for short, has long existed in wireless communication literature as a concept. In SWIPT, we are faced with a hard decision, and that decision is how we split the power between the information receiver and the rectifier, which converts the incident radiation into useful DC power, which ultimately powers the whole system. In our work, we proposed the first antenna which allowed us to perform SWIPT across two different frequency bands using a Rectenna which does not need an impedance matching network. And this design is based on a simple microstrip patch antenna, and we implement it using flexible materials, using e-textile conductors for wearable applications.
Here at Southampton we do a lot of work on electronic textiles, which is where we put electronic functionality into otherwise standard fabrics, and a consistent challenge with these systems is powering them, and they all too often rely on rigid conventional batteries for their supply of power. The work we've done on energy harvesting, and in this case RF energy harvesting, is an essential ingredient towards making these systems autonomous and removing that requirement for rigid power supplies. Another requirement is obviously supplying or communicating the data from these systems. And the work we've done in this paper is both tackles the energy harvesting aspect as well as the communicating the data as well.
Starting with a simple microstrip patch antenna, and just like any other wearable antenna, our antenna can operate on the human body and communicate with a high gain in radiation efficiency and complying with the absorption limits. The novelty in our design comes from how our second port of the antenna is integrated. Our port uses an inductive loop and dipole-like radiating arms. And thanks to the inductive design of the second feeding port, we do not need a matching network, so the complexity is significantly reduced and the cost is significantly reduced. And in terms of power conversion efficiency, our design compares very well to state-of-the-art Rectennas. In fact, it improves the efficiency by more than 50%. We have shown that the same topology can be applied to more complex antennas, meeting the requirements of different wireless communication applications. We have demonstrated that SWIPT could happen in the same band and not just over two different bands, using a 4-port microstrip antenna, which combines the benefits of dual polarization communications for MIMO systems and full duplex with the convenience of dual polarization power transmission, where we do not need to care about the alignment between the transmitter and the receiver. We believe that using our array of SWIPT antennas, wireless-powered networks, wireless-powered body area networks can take a big step forward in integrating them in future real-world applications based on multi-band and multi-polarization diversity antennas.